Episode 15, Nonlinear Systems and Multivariate Newton's Method. So we've previously looked at Newton's method for a single equation of a single unknown. Today we're going to use some linear algebra skills to help us extend that to approximately solve a nonlinear system of n unknowns and n equations. So that's going to take the form of some function f1 of x1, x2 up to xn equals 0, and then a second equation f2 of f2 of x1, x2 up to xn equals 0, and then down to fn of our unknowns. But I'm going to think of this exclusively in a vector function equation, f of x equals 0, where everything's a vector. And so f is a vector valued function that maps a vector in Rn to another vector in Rn. Okay, so let's review Newton's method a little bit here. We were trying to solve a single nonlinear equation, f of x equals 0, and we did that by making an initial guess and then forming the tangent line around that solution. Right, that's the best linear approximation of the function near that value. It's easy to solve for where a linear function is equal to 0. Right, we just have f of x naught plus f prime of x naught times x minus x naught equals 0. So we get x1 equals x naught minus f of x naught divided by f prime of x naught. And then we just repeat this, right? We plug x1 back into this formula, so x2 is x1 minus f of x1 divided by f prime of x1. So now, let's try to follow this template, but extending it to a vector-valued function, not a single scalar equation. All right, so we have our f of x equals 0 that we want to solve. Right, we can still make an initial guess. That's now a vector, no problems there. Now, if we linearize it here, this is where it becomes a little bit more complicated, right? Instead of the tangent line, we need to think of this tangent n-dimensional plane analog, right? So f of x is approximately f of x naught plus this df, the Jacobian of f at x naught, times x minus x naught, where the Jacobian, df, is the matrix of all the different first partial derivatives of f. Right? So we have, on each row, we have the partial of the first function with respect to each of the individual variables. Right? So we get the partial of f1 with respect to x1, partial of f1 with respect to x2, and so forth. Then the second row does the same thing to the second function in f. And then down to the last row where we have the last function, the partial with respect to x1, then the partial with respect to x2, and so forth. Right? So this, what was a scalar equation, becomes now a vector equation that we need to set equal to 0. All right, well, the first step's pretty easy. We can just subtract f of x naught from both sides. No problems there. Now, whereas with just Newton's method, we would divide by the derivative, we can't do that here. We have to multiply by the inverse of the Jacobian. Right? It's an n by n matrix, and so we have to invert that, right? And then once we do that, now we can add x naught to both sides. So we get that x, or what's going to be x1, right, is x naught, our initial guess, minus the inverse of the Jacobian evaluated at x naught times f of x naught. Right, so it's the same kind of idea as Newton's method, but it's a vector version of that. And so that's what multivariate Newton's method is, right? We want to solve f of x equals 0. We pick our initial guess x naught, and then xk plus 1 is equal to xk minus the inverse of the Jacobian at xk times f of xk. Right? And we do this until we converge. So like we had with single variable Newton's method, multivariate Newton's method is also quadratic. What exactly do I mean by that? So if the true root is r, we would expect the limit as x goes to the limit as k goes to infinity of the infinity norm of xk plus 1 minus r divided by the infinity norm of xk minus r squared to equal L, some non-zero constant. Right, so the error here is with respect to a norm. You could have used the 2 norm, you could have used another norm. Here, the infinity norm is typically going to be the best because that focuses on the largest error of a single element. Right? The squared there in the bottom is where we get the quadratic. Now, like with single variable Newton's method, multivariate Newton's method might not actually give us quadratic convergence for every function, every equation, right? Like with with the single variable Newton's method, right? It was if the derivative at the root was 0. The analog here is if we're converging to a root that makes the Jacobian be a singular matrix. Right? That's where we're going to see the slowdown and see only linear convergence. When we code this up, we need to have some kind of test for convergence. So we would do something kind of similar of comparing the previous iterate with our new iterate to see if it's changing, but we will have to use one of the norms to do that. So we'll use the infinity norm here. And so we're going to look at the infinity norm of xk plus 1 minus xk. And so when we do that in MATLAB, we'll need to store both of those iterates. We'll have to keep those around in order to compute the norm, right? So we want a while norm of xk plus 1 minus xk, and the infinity norm. While that's greater than our tolerance, we'll keep going. So I want to close with a brief example of this in 2 dimensions here. So I want to use multivariate Newton's method to solve the equation u cubed plus v squared equals 4 and u squared minus 3uv plus 3v cubed equals 5. And so this is a nonlinear equation. So this is a nonlinear system of 2 equations and 2 unknowns. Right? So we need to put it first into the form of f of x equals 0. So my x vector here is uv. And the first equation is going to be u cubed plus v squared minus 4. And then the second one will be u squared minus 3uv plus 2v cubed minus 5. Right? Those are 2 functions that, when they're equal to 0, we have a solution to the system we're trying to solve. Now we need the Jacobian of this function, right? So the Jacobian, the first row, so we have 2 equations and 2 unknowns, so our Jacobian is going to be a 2 by 2 matrix. The first row is going to be the partials with respect to the 2 variables of the first equation, right? So the partial of u cubed plus v squared minus 4 with respect to u, that's 3u squared. The partial with respect to v is 2v. For the second equation, u squared minus 3uv plus 2v cubed minus 5, the partial with respect to u has 2 terms, right? It's 2u minus 3v, and then the partial with respect to v is minus 3u plus 6v squared. So that's our Jacobian. Okay. So I've got those down at the bottom. Right, so if we use an initial guess of 1, 1, right, we get our x1, our u1 and our v1 as u naught v naught minus the inverse of the Jacobian at u naught v naught times f of u naught v naught. So that's 1, 1 minus the inverse of the Jacobian at 1, 1 times f of 1, 1. Right? So we need to know what those are. All right, so when we plug 1, 1 into the Jacobian, we get 3, 2, minus 1, 3, but we need to invert that. And then when we plug 1, 1 into our function, we get negative 2, negative 5. And then we're subtracting that product from 1, 1. Right? So the inverse of 3, 2, negative 1, 3 is 3, negative 2, 1, 3 divided by 11. So u1, v1 is going to be 1, 1 minus 1/11 times 3, negative 2, 1, 3 times negative 2, negative 5, right? And that becomes 7/11, 28/11. And so that's our first iteration, right? So we would look at the norm of the difference between x1 and x0. That's 1.4545. That's going to be bigger than our tolerance here, right? That is the infinity norm. So here I've converted that to a decimal representation. And then if I keep on going, if I plug in u squared, if I plug in u1 and v1 into the formula to get u2 and v2, I get here, my norm comes down to 0.5951. Keep on going, it goes down to 0.233, right? 0.0520, right? It's coming down, and then down to 0.0019, and then the next one's down to 10 to the minus sixth. And so we're seeing the acceleration that we would expect to see with something that exhibits quadratic convergence. All right, so we'll code this up in class.